Good morning, everyone, and thank you for joining us. Before we start, I want to ask you a simple question. If a vial of your product shed a single glass flake into a patient's sieve line, would your quality team know about it before the patient did? That question sits at the heart of what we are covering today. Glass delamination has triggered some of the most expensive and reputation-damaging recalls in the pharmaceutical industry over the last decade, and in almost every case, the risk was predictable long before it became a crisis. Over the next few minutes, we are going to walk through exactly how to predict it, detect it, and prevent it, using the framework laid out in USP General Chapter 1660. Let's get started. Today's session is called Evaluating Inner Surface Durability of Glass Containers per USP 1660. This is a practical, working session, not a theoretical one. My goal by the end of the hour is that you walk away knowing exactly what questions to ask your glass supplier, what tests to run before you commit to a container, and what red flags should stop a program in its tracks. Here's our roadmap for today. We'll start with the fundamentals, what delamination actually is and why regulators care so much about it. From there we'll move into the compendial framework, the manufacturing side of glass, the root causes that actually trigger delamination, and then the practical heart of the session, how USP 1660 recommends you screen for it, and which analytical techniques give you the clearest picture. We'll wrap up with 2 real-world case studies and a set of mitigation strategies you can take back to your team this week. Let's start with the basics. Delamination is what happens when the inner surface of a glass container chemically breaks down and sheds thin, shimmering flakes called lamellae directly into the drug product. Here's the mechanism, step by step. First, alkali ions like sodium and potassium leach out of the glass surface into the solution. Second, that repeated leaching depletes the structural network of the surface layer. Third, what's left behind is a weakened, silica-rich layer that becomes brittle over time. And fourth, often months or even years into the product's shelf life, mechanical or thermal stress causes that brittle layer to flake off. Why does this matter so much? Because unlike a lot of quality issues, this one is a direct patient safety hazard. Glass particles in an injectable product are not a paperwork problem, they are a needle in the vein problem. And that's exactly why this topic gets the level of regulatory attention it does. So where does this sit in the regulatory landscape? USP Chapter 660, no, 16, just 660 classifies glass containers into types 1, 2, and 3 based on chemical durability. USP 1660, our focus today, is the newer chapter that specifically addresses predictive screening for delamination risk. In Europe, the equivalent guidance lives in Pharmacopoeia Chapter 3.2.1. And I'd be doing you a disservice if I didn't mention the FDA's recall history here. Several high-profile parenteral recalls over the past decade are what pushed USP to formalize this guidance in the first place. It's also worth knowing that testing labs doing this work are increasingly expected to carry FDA registration under GDUFA. Regulators are not treating this as optional anymore. Now let's talk about where the glass itself comes from, because manufacturing history matters more than most teams realize. There are 2 manufacturing routes, molded glass, which is pressed or blown from molten glass and typically used for bottles and vials, and tubing glass, which is drawn from tubing and used for ampoules, cartridges, vials, and pre-filled syringes. On the composition side, borosilicate type 1 is the industry standard for parenterals because of its high chemical resistance. Soda lime silica types 2 and 3 is lower cost but also more prone to delamination. Here's something a lot of teams overlook: furnace condition matters. The refractory bricks lining a glass furnace degrade over its operating lifetime, and that degradation can subtly affect glass quality, which means the durability of your container can vary batch to batch, even from the same supplier, if you're not tracking furnace age and maintenance history. So what actually triggers delamination in the real world? 5 factors show up again and again. High fur or citrate and phosphate buffered formulations are aggressive toward glass and accelerate attack on the surface. Terminal sterilization by autoclave heat plus moisture significantly increases leaching. Extended storage duration compounds what is otherwise a slow degradation process into something that becomes visible over a 2 or 3 year shelf life. Elevated storage temperature accelerates the underlying ion exchange reaction. And finally, that furnace variability we just discussed introduces batch-to-batch differences that can catch teams off guard if they assume every lot behaves identically. If you remember one thing from this slide, delamination risk is never just about the glass. It's about the specific interaction between your formulation chemistry and that particular glass surface. This is where the chapter gets genuinely useful. USP 1660 recommends 3 accelerated attack solutions for screening: 0.9% potassium chloride, which simulates mild aqueous attack, 3% citric acid, which simulates aggressive low-FA conditions, and 20 millimolar glycine, which simulates amino acid-containing formulations. What are you actually measuring when you run these? Elemental leaching of silicon, aluminum, and boron into solution. The silicon to aluminum and silicon to boron ratios, shifts in inferent conductivity, and any visible pitting or surface change. You compare these results across different containers, different manufacturers, and different processing conditions to rank durability before you commit to a container for your program. One caveat worth flagging to your team: the chapter tells you what to measure, but it does not prescribe exact sample sizes or a rigid study design. That part is left to your risk-based judgment, which is exactly why having an experienced analytical partner matters here. Let's get specific about the tools. DIC microscopy, differential interference contrast, is your early warning system. It reveals surface pitting before it's visible to the naked eye. Same with energy dispersive X-ray, or SEMEDX, lets you characterize the actual flake morphology and composition once something has formed. For the solution chemistry side, ICP-OES or ICP-MS quantifies dissolved glass ions, silicon, aluminum, boron, sodium in your extraction solution. Particle analysis, following USP chapters 788 and 789, sizes and counts visible and subvisible particles. And simple FA and conductivity tracking gives you an early, low-cost signal that something in the solution chemistry is shifting. The practical takeaway: no single technique tells the whole story. A defensible screening program combines a surface technique like DIC or SAME with a solution chemistry technique like ICP. This next piece is what separates a generic screening exercise from a study that actually protects your specific product. Propensity pre-screening was introduced into USP back in 2013, and it assesses delamination risk across the container's full life cycle under real, in-use conditions. It's specifically designed to compare variability across manufacturers, glass formulations, batches, and post-forming treatments. Here's the key distinction: model solutions, the KCl, citric acid, and glycine we discussed, are excellent for standardized apples-to-apples comparison across suppliers. But at some point, you need to test your actual drug product in its actual container, because that's the only way to confirm how your specific formulation really interacts with that specific glass surface. Screening data tells you about risk in general. Interaction studies tell you about risk in your product. Let me bring this to life with 2 contrasting stories. Case 1, a high-FA injectable product was stored in soda-lime glass and visible flakes weren't detected until after the product had already been distributed. No predictive screening had been performed against the actual formulation before launch. The root cause, when the investigation was complete, was almost embarrassingly simple. The glass type had been selected based on cost, not chemical compatibility with the formulation. Case 2 tells a very different story. A team ran propensity pre-screening using the actual drug product before commercial launch, and it flagged elevated silicon leaching in one supplier's lot. That early signal prompted a switch to delamination-resistant glass before a single unit reached a patient. The result: the container was switched pre-launch, and there have been 0 delamination complaints post-market. Same underlying risk, completely different outcome. The only difference was whether screening happened before or after launch. So what do you actually do with all of this? 6 strategies, in rough order of how early you'd apply them. Delamination-resistant glass specially treated borosilicate engineered for a low delamination factor is your strongest first line of defense. Inner surface coatings, like silicon dioxide layers, act as a physical barrier against ion exchange. For some programs, alternative materials like cyclic olefin polymer or copolymer containers sidestep the glass risk entirely. On the process side, rigorous supplier qualification with real change control and lot-to-lot durability testing, ongoing monitoring through periodic rescreening across your product's commercial shelf life, not just at launch, and formulation-aware container selection, where the glass type and treatment are matched deliberately to your specific foreign buffer system rather than chosen by default. None of these as a silver bullet on its own. The programs that stay out of recall territory typically combine at least 2 or 3 of these strategies. That brings us to the end of our session, but I want to leave you with something practical, not just informational. If you're currently selecting a glass container midway through a stability program, or you've had a delamination scare and you're not sure how serious it is, let's discuss. We'll look at your specific glass and formulation pairing and flag the likely risk areas, no cost, no obligation. Thank you all so much for your time today. If a question comes to mind after we log off, don't hesitate to reach out directly. My contact information is on the final slide. Glass delamination is one of those risks that's completely manageable when you catch it early, and completely unmanageable once it's in a patient's hands. I hope today gave you a clear, practical path to make sure it's the former, not the latter. Thank you again, and I look forward to speaking with many of you one-on-one.